Okay, so let's talk about 3 different ways to deprotonate a terminal alkyne. So what's a terminal alkyne?
That's the one with the H at the end, yeah.
That's one with an H at the end. So number of carbons, 1, 2, 3. So there's 3 ways. So we're gonna need a really strong base because this CH bond, while it's acidic, it's not a very strong acid, right? It's weakly acidic. Its pK is like 25. So it's not a very strong acid. It's actually less acidic than water, but it still can be acidic. So we're gonna need a pretty strong base, reactive base, to make that become deprotonated, right? To break this CH bond, we're gonna need a pretty strong base. And there's 3 different options that you'll see. First one is Na, NH2. A lot of times you'll see it drawn like that, but once you see Na, sodium, it's on the far left side of the periodic table, you should automatically draw a plus charge and then put a minus charge on the NH2, right? Go back to those, how many bonds does nitrogen want to have, right? If it does have 2, it has a negative charge. So that's one possibility. Another possibility is something called N-butyl lithium. So you'll see it like this. So carbon 1, 2, 3, 4. Now if you look where lithium's at, it's just right above sodium. So again, you should be thinking, well, that's a plus charge, right? So even though there's a bond there, really, another way to draw this would be lithium with a plus charge, and that carbon 1 would have a negative charge. 1, 2, 3, 4. So carbon with a negative charge, that would be another option. So these 2 are kind of the same. There's 1 and 2. The third option, so there's option 1, option 2. The third option is very similar to the second option. It's something like CH3 MgBr. So 3 there. Or you could draw it where it's CH3 with a minus on the carbon and then a plus on the magnesium. Now magnesium, again, where's magnesium at? All right, it's still the far left side of the periodic table, right? It's not going to have a covalent bond to carbon. So the third option here, right, again, either we have a negative charge on a carbon or a negative on a nitrogen. So the carbon one we should look at and be like, wow, that must be really reactive. Carbon is not very much a negative, right? So that's really going to take that hydrogen pretty easily. Nitrogen also, right, and it's not like nitrogen, you see a lot of nitrogen with a negative charge either. That's also pretty reactive. So now what does this look like? So it's just an acid-base reaction. So all these cases, I'm just going to say you could have a couple different things. Let's do the NH2 minus. So you have the NH2 minus. It's going to be the same mechanism either way. I can do another one down here. It'll look the same, right? If I did the N-butyl lithium one, carbon with a negative charge, the mechanism is going to be the same. Electrons go there. Those carbon 1, 2, 3. Carbon 1, 2, 3. Negative charge comes, takes that. So what do you get? Actually, these are one-way streets in this case. There's a reason why for both of these. So negative charge there. Get to this acetylide ion. NH3 plus butane, right? So we added, so again, this carbon right here is bonded to a carbon and then 2 other hydrogens. They're not drawn in, but they're there. So then at the end of the day, it ends up with a new hydrogen, the one it took from the alkyne. Right? So make sure we're recognizing, right, that's a carbon, a CH3, that's a CH2, that's a CH2. This is a CH2, but that carbon has a negative charge. So when it grabs that H, now that carbon, right, if I numbered these carbons, 1, 2, 3, 4, 1, 2, 3, 4. We're grabbing that H right there. And you end up with butane and ammonia, and both of these are actually gases. So why are these reactions one-way streets? All right, most acid-base reactions are equilibrium, but equilibrium reactions can be shifted if one of the products is a gas and it would bubble out of solution. So that's how we help drive this reaction actually is. And you can imagine if I use CH3 minus, that would make CH4, that's methane, also a gas. So it would also help drive this reaction by one of the products bubbling out. There's 3 ways to deprotonate a terminal alkyne. Make sure I add those numbers in, 2, 3, 1, 2, 3. And I've talked at length about why, of course, this CH bond is acidic. You refer back to a hybridization and acidity tutorial. That's also on YouTube. So now once you have this carbon 3 is a good nucleophile. It's electron rich. It can attack electrophiles, and you can imagine all types of electrophiles it could attack then at this point. It could do substitution reactions, one of the major ones. So let's take a look at a terminal alkyne, same one we've been kind of using. So a terminal alkyne with a CH. So when you look at this, carbon 2 and carbon 3 are different. Carbon 2 is bonded to 2 other carbons. Carbon 3 is bonded to a carbon and an H. Right, so it's terminal alkyne. So they're different. Now there's two. You should be able to make different things from this. So one of the things, right? I mean, you can make would be a ketone. The other thing you can make would be an aldehyde. 1, 2, 3. 1, 2, 3. Now, as you look at this, and you maybe say, well, what reagents would go in for each thing? You want to ask yourself, okay, there's carbon 2 and carbon 3, 2 and 3. How do I mean, so basically, either something's going to happen on carbon 3 or something's going to happen on carbon 2. Right? Carbon 2 is the more substituted carbon. Remember, we think about Markovnikov maybe type stuff. Right? That's regioselective. Which kind of reagents are regioselective for carbon 2? So I can think of 2 ways to make this, but I can only think of 1 way to make this aldehyde where whatever we're adding ends up on the less substituted carbon. So I can think of 1 way to do this and 2 ways to do that. See if you know those.
Yeah.
So the first one, or the second one, if we're just trying to make the anti-Markovnikov one, the set of reagents, it's a 2-step process. Step 1 is a BH3, or a boron of some sort. Sometimes you see it weird. B2H6, sometimes there's like silane boron. Anytime you see boron, that's what's going on. The second step, you replace the BH3 with an OH minus, H2O2. Right? Again, this step, of course, is a syn addition. So it's regioselective. It selects for the less substituted carbon, but it's also a syn addition. The boron and the H add syn as well. So that's one. That's how you get that. Now there's 2 ways up top. The one way is just H plus in water. So that's one set. Another set that would work would be Hg2 plus in water, and usually they put acid as well. So there's 2 different sets of reagents, 1 set, 2 sets of reagents to actually make this happen as well. Now both of these come from, oh boy, right? A minor product, so these will both be the major products. Both of them come from a minor product, enol, right? So in either case, the enol is going to look different, right? Enol, alkene with an alcohol, enol. For the bottom one, the enol would be with the OH here, and the H that added, right? This is important. It's important to show that syn, right, that this H and this OH are on the same side, that enol. Right? You can't tell when it goes to the aldehyde, but before that, you should know that. And the top one, again, an alkene, but now instead of being, right, if it was on 1, 2, 3, the alcohol is on 3, now the oxygen or the alcohol part is going to be on carbon 2. And in this case, it depends, right? Usually with these, this is some sort of an anti-addition, right? It's an anti-addition. Now in this case, it doesn't matter because there's a hydrogen here. So you're adding an H and an H. But this comes from an anti or trans addition, right? That H plus or mercury adding, mercury makes a 3-membered ring. H plus makes either that 3-member ring with hydrogen, or we can do it all in one step, but it's always an anti-addition. Now, it doesn't matter here because, right, these are both H's. So a terminal alkyne you can't tell. But if it was an internal alkyne, you would be able to tell that this was an anti-addition. So this is the enol that is the minor product for this ketone that's found in both these reagents, and this is the enol that's found with the BH3 from this aldehyde. All right, so let's take a look at a terminal alkyne, and we're gonna have it react in 2 different steps, so 2 different reagents. The first step is gonna react with Br2, so 1 mole of Br2, and the second step we're gonna react with Cl2, but it's also in water. All right. So the first step, add in our lone pairs. Hopefully we're doing that by now. Numbered our carbons. Nucleophile is gonna be the pi bond, so that reacts there. Breaks the bromine-bromine bond, and then this other bromine lone pair comes back down. We make that 3-membered ring. Still a pi bond there. Be super duper careful with our bond angles here. This is sp2 hybridized. Make sure these need to be down. Don't make some weird bond angles. And we also made Br minus. So now we have a choice, carbon 2 or carbon 3. Where's the bromine going to attack?
Carbon 2.
Carbon 2, the more substituted one, that's right. It's more stabilized, more delta plus there, because it has more hyperconjugation, you can kind of think of it that way. That breaks this carbon-bromine bond. This should be equilibrium too. And that, of course, is a trans addition. Be very careful with your bond angles again. The bromines are opposite each other. 1, 2, 3. So we get that one intermediate, we get that trans addition. Right? So it's regioselective, it's selecting for that carbon, the more substituted carbon, and the stereoselectivity is always a trans addition. Good. So now the second step, we're going to take our alkene, and we're going to react it with Cl2. But we're reacting it in water. So this is very similar to reactions we've done last unit, right, in unit 3. So again, pi bond attacks the chlorine chlorine bond breaks, lone pair comes back down. Now in this case, we gotta get those wedges and hatches out again, because we're doing alkenes. So this shows the bromines are on opposite sides of the alkene, so one should be wedged and one should be hatched. If we number the carbons, 1, 2, 3. I'm only going to show one enantiomer of this because I can. So this chlorine, right? This alkene is flat, so the chlorine could be on the top or the bottom. So I'm just going to show one of them. Right, we also could draw the enantiomer of this, the other version of this, where the chlorine would be down. So we have Cl minus. So now we have carbon 1 or carbon 2. Which carbon do you want to attack? Which one's the more substituted one? 2. So let's go there. And it's going to be, of course, again, what kind of addition? Trans or anti-addition.
So why are we taking the Cl if water is an
Oh! Forgot about my water. Whoops. Let's do that. Water's in there. Let's have water do the work. Right? Water is, of course, much more concentrated. Let's have water do that. So now what do we have? So the chlorine's there. Notice, don't skip steps. Did I break an OH bond in this step? No, I did not. All I did was take a lone pair from that oxygen and have it add. 1, 2, 3. Plus I need to balance my charge anyways. Let's see. Plus. There still should be a Cl minus floating around, right? I ended up not using that here. To balance my charge from over here, there's a plus and a minus. That's net neutral. Plus and a minus, still good. Now you can either have the chlorine come and take the H, or you can just have the H fall off. It's up to you. Either way is fine, right? Because HCl is the same as H plus Cl minus. It's a strong acid. So what does the final product look like?
So you could draw an arrow just from this, like from the minus and the Cl and bring it to the H.
Yeah, you could do this if you wanted to, or you could just have the H just falling off,
Oh, okay.
right? Because HCl is the same as H plus Cl minus. So the final product would be bromine, sorry. One, two, three. There you go. So that'd be the final product. So you can see a lot of things here. You actually made, let's see, did you make 2 asymmetric centers? You did. You actually make 2 enantiomers. Right? You'd make this, and then the other version, what would you have made? You'd also make, it's an enantiomer. What's the enantiomer look like?
Switches.
All you gotta do is flip which one. Let's just make sure we do it right. The CO will be pointed down, and here the alcohol would be OH, right? So you make both those. These are enantiomers to each other. They have 2 asymmetric centers, right? There's 2 asymmetric centers here, but they're both opposite. Everything's opposite. That means they're enantiomers, right? Everything's opposite. They're enantiomers. Let's take this, and we're going to label these into maybe a free energy diagram. So I'm going to label. So we have starting material. I'm going to call this IA as an intermediate A. Intermediate. This is intermediate B. Intermediate C. You're welcome. Intermediate D, and then products. Let's say that delta G is negative in this case. So what's it going to look like? Let's do it like this. Let's do starting materials. And I know delta G is negative, so the product's going to have to be lower, right? So there's a difference there. Let's see if I can do... Oh, man. Kind of stuck. Yeah, let's just get it all the way. I'm going to redo it. Hopefully you have those things written down. So starting material, product needs to be lower because the delta G was negative, so we're going downhill. Intermediate A, what the heck was intermediate A again? That was a bromonium ion with a Br, the plus charge. That's probably going to be pretty high in energy, right? 3-membered ring. So we'll put that IA there. Let's see what else do we have. IB was an alkene. That's probably pretty low in energy. Let's put that down here. IC was a CL with a 3-membered ring. That might be a little bit lower than the IA just because, or IC, sorry, C. That might be a little bit lower just because this has a alkene in there, so it's making a little more angle strain than without an alkene. And then ID is just a oxygen with a plus charge, but that's pretty easy to fix. Certainly not as bad as a 3-membered ring, so I'll put ID. Intermediate D there. Add in all our things. Woo! Whoop! Whoop! So we have 4 intermediates. Oh, yep, 4 intermediates. That means we have 1, 2, 3, 4, 5 transition states, right? So that's how I'd map that out.